Hello everyone, my name is Salim. I am a senior facility technologist working at National Nanofabrication Center located at Center for Nanoscience and Engineering, ISC, Bangalore. Today I will be briefing you about the various tools and the capabilities which are available at an NFC and which is grouped under Diffusion and Inline Characterization Bay. So starting with Diffusion Bay, so we mainly have furnace systems which are for deposition, diffusion and annealing. So you see the one to your extreme left is a deposition tool, the middle one is for oxidations and diffusion, and the one to the extreme right is meant for annealing. So each of this furnace system consists of 4 horizontal furnace tubes wherein each is dedicated for a specific process. We will be having a look at each and every process in detail in the upcoming slides. So coming to the furnace construction, it mainly consists of a quartz tube which is surrounded by heaters which will supply the heat required for gaining the high temperature. At one end of these furnaces you have your precursors such as oxygen, nitrogen and the respective reactants required to have the reaction. You have your wafers placed in this orientation inside your furnace, and on to the other end of your furnace you have exhaust system which is used to take out any byproducts which are generated during your process. Next, coming to oxidation. So under oxidation we mainly have two kinds of oxidation. So one is called as dry oxidation, which mainly relates if you have oxygen as an oxidizing source. Okay, so below is a schematic how it explains. You have your oxygen molecule which will interact with your silicon at high temperature to form an SiO2 bond, and this oxide starts to build on top of your silicon surface. This oxide is used as a gate dielectric or sacrificial oxide in your semiconductor fabrication. The next oxide is used by pyrogenic oxidation, which uses water vapor as an oxidizing source. So under this case also you have SiO2 but along with a generation of hydrogen. Hydrogen being a gas escapes from the furnace and SiO2 starts to grow on top of your furnace. And this slide. Okay. Yeah. So coming to oxidation, so we mainly have two kinds of oxidation. One is dry oxidation, the other one is pyrogenic oxidation. So dry oxidation relates to using oxygen as an oxidizing source, and pyrogenic relates to using water vapor as an oxidizing source. So under dry oxidation you mainly use it when you are looking for applications like gate dielectrics or sacrificial oxide, and pyrogenic oxidation is mainly employed when you are looking for a thicker oxide to serve your isolation purpose or as a mask for dopant or a field oxide application. Next, coming to diffusion. So diffusion mainly relates to doping, wherein you introduce impurities in your semiconductor to alter its electrical properties. So by doing this you can either make it to behave as a conductor like an electrode, or you can make it to behave as an insulator to act as a resistor. This is performed by introducing the impurities into your silicon. The two impurities that we have at an NFC, one is boron, which is a p-type dopant for your silicon since it has only 3 valence electrons, and phosphorus is an n-type dopant which has 5 valence electrons in its outermost shell. So by introducing these dopants you can change your electrical properties of your silicon, and in order to ensure that you introduce these dopants only in a specific area, you need to mask or you need to create a template for that area, and that is done by using oxide or nitrate as a mask. Since we use a very high temperature for performing this diffusion, so any other material other than oxide or nitrate may not be able to withstand. For these conditions we use oxide or nitrate as a dopant mask, and whichever region wherein you have the nascent silicon exposed, only those regions the dopants shall get impure. Only in those regions the dopants will have an interaction with your silicon. Next, coming to annealing. So annealing is a heat treatment process which is used to enhance your properties of your material either in terms of compositional, electrical or physical. So this is mainly used to relieve stresses in your thin film, to have a reflow of your materials, also to have a deeper or at high depth dopant diffusion. So coming to the tool capabilities, so these tools are mainly used for processing up to the temperature of 1100 degrees Celsius The sample size can be starting from a small 1 cm sample to a full 4-inch wafer can be processed. And an advantage of furnace is that you can do batch processing. So together you can process 25 wafers in a single batch. Since mainly these furnaces are level 1, so thereby RCA cleaning is a mandatory for these furnace systems. And coming to specific process capabilities, so dry oxidation is used when you are looking for the oxide thickness starting from 10 nanometer to 150 nanometer. Pyogenic is used when you are looking for oxide thickness in the range of 150 nanometer to 1 micron. And coming to doping, you can have both phosphorus and boron doping if you are looking for a resistance range in terms of 5 ohms per square up to 300 ohms per square. And coming to annealing, so annealing mainly you are looking for different ambients of annealing. So you will be having nitrogen, oxygen, argon and forming gas. So forming gas is generally a mixture of hydrogen and nitrogen. So next, coming to RTP. So RTP stands for rapid thermal processing, wherein you are reaching a very high temperature in a very short duration of time. And this is performed by making use of lamps or lasers as a heating source. So in this slide you can look at the various RTP systems that are available at an NFC. So we have system 1, which is a level 4 tool which is meant only for annealing. We have system 2, which is a level 1 tool and it is meant only to perform oxidations. Coming to the capabilities of these RTP systems, so they help you to have a very high ramp rate up to 30 degrees per second. You can reach higher temperatures similar to furnace of 1100 degrees Celsius. The process can be faster, you can have a better control in a very short duration of time, and by doing this you will have a very low thermal budget. And coming to applications, so similar to furnace, these RTP tools can also be used to do annealing, oxidation, nitridation, silicidation, etc. So next, coming to LPCD. So LPCD stands for low pressure chemical vapor deposition tools. So under this we have different tools to deposit different materials. So it could be a dielectric material, it could be a semiconductor, or it could be an insulator. So coming to the mechanism, so this slide illustrates the deposition mechanism that takes place in a CVD tool. So as you can notice, so you will have a gas stream which will mainly carry a precursor or the reactants. The reactants from the gas stream needs to initially diffuse through a boundary layer, reach your surface of your substrate, wherein it needs to adsorb on the surface. Once adsorption is done, the reactant will either decompose or will have a chemical reaction, after which it will form the respective material. So once this material is formed, then the respective byproducts which are generated as part of this process dissolve from the surface and is carried out in the exhaust stream. So this is how deposition happens. So coming to the different materials, so the first material is LPCD silicon nitride. So this is formed using dichlorosilane and ammonia as a source for this process. So this process can be used to have a thin film ranging from 20 nanometer up to 200 nanometer. And coming to applications, this is mainly used in MEMS and NEMS as a structural layer. It is used as an anti-reflective coating in your solar cell as well as a mask for wet etching process. Below what you are seeing are some of the applications wherein this LPCD silicon nitride is used to fabricate your cantilevers and simply supported beams. Next, coming to semiconductor deposition in LPCD. So speaking about semiconductor, so we have capability to deposit silicon and germanium and a combination of silicon germanium. So as this is a semiconductor, so you can also have a dope form of this by introducing the dopants, and this technique is called as in situ doping. So under in situ doping, you are basically allowing your dopants to flow along with your deposition gas, which will form a compound while your silicon or germanium is getting deposited. So coming to the dopant source, you have p-type dopant using diborane and you have n-type dopant using phosphine, which basically decomposes to form boron and phosphorus respectively. So this thin film can range from 40 nanometers up to 3 microns. So along with this semiconductor thin film deposition, there is also an application wherein we use this to form silicon nanowires. So the below image shows you the silicon nanowire growth. This growth is done by the help of vapor liquid solid, which is known as a VLS method. wherein you use a very thin seed layer which will serve as a reference to grow your nanowires. So these nanowires can range from 35 to 200 nanometers and the length can vary in terms of microns. Next, coming to LPCD SiO2 deposition, which is generally called as low temperature LTO oxide. So this oxide is generally done at a temperature of 450 degrees Celsius with a reaction between silane and oxygen. So this SiO2 can be up to 1 micron, starting from a lowest thickness of 100 nanometers, and the surface non-uniformity across the wafer can be less than 5%. So during the deposition of this oxide, you can either make it a doped oxide or an undoped oxide. So speaking about doped oxide, you have two forms. One is called as BSG, borosilicate glass. The other one is PSG, phosphorus silicate glass. And this is done by introducing the dopants during your oxide deposition. So for P-type, you have diborane, which will form your BSG. And for N-type, you have phosphine, which will form your phosphorus silicate glass. This slide relates to the contamination levels of the tools that are available at diffusion bay. So we mainly have level 1 tools which are meant for oxidations and diffusion. Level 2 tools are mainly for depositions. So it could be the deposition of a dielectric like silicon nitride and oxide, or it could be deposition of semiconductor, which is silicon or germanium. Level 3 mainly illustrates the deposition of semiconductor along with the nanowire growth and the different annealing furnaces which are meant to anneal metals or a combination of a metal and a dielectric. Level 4 are mainly dedicated for the tools wherein you can have the samples from a different contamination levels, and this are mainly the last step annealing process that you will be doing during your fabrication. So under this we have grouped it into RTP and PZT, contaminated tempers. Next, coming to inline characterization bay. So under this bay we mainly have tools to do measurements or to perform various characterizations on your samples. So under this, the tools that are available are ellipsometer, DECTAC, microscope, KMOS Ultrascan, 4-point probe and lifetime measurement tool. So since these are the measurement tools, so thereby they are not classified under any contamination level. So thereby all the tools available at inline characterization bay are level-less. So coming to the first tool, which is ellipsometer. So this is an image of an ellipsometer tool which is available at an NFC. So coming to capabilities, so this tool is mainly used to measure the thickness as well as optical constants of your thin film. The above image illustrates how this measurement happens. So you have a polarized light which is incidence on your sample, and you will have elliptically polarized light. So each and every material will have its own characteristics elliptical polarization. By studying or analyzing this polarization, we will be quantifying the data in terms of thickness and optical constants. So this system is mainly a single point measurement tool, and you have a very wide wavelength range from 245 nanometers to 1 micron. You have a focusing option wherein if you have a pattern sample, you can differentiate between your thin film on a planarized region or onto your features. And lastly, this tool can be used to measure thicknesses up to 10 micron if it's a transparent dielectric film, and 30 nanometer if it's a metal film, which is mainly acts as an absorbing layer. And lastly, the sample size can range from a small 1 cm sample to a 12-inch full wafer. So this slide illustrates the different materials which are measured using this tool. Okay, so you have oxides, nitrides, you have metallic films, you have ITO, HFO2, etc. Next, coming to DECTAC, X-ray surface profiler. So this is a tool which is used to measure your step height or etch depth as well as roughness of your sample. So this tool has an option for both 2D as well as a 3D profiling. This slide illustrates how the measurement happens. So you have a stylus. The displacement of the stylus is recorded by a sensor, and that gives you the output data of the variation of your topography or waviness on your surface. So this tool is used to measure your topography as well as roughness either in a 2D or a 3D mapping option. So since you have a stylus which needs to be in contact with your sample, so we have a force range from 0.03 milligrams to 15 milligrams. This is mainly used to facilitate different forms of your sample. So if your sample is soft or slightly has a very low resilience, then you can have a different magnitude of force. Here the force is mainly used to ensure that you have a contact with your sample. Coming to stylus options, so you have two stylus options, one is 2 micron and the other one is 12.5 micron. And coming to the length of the scan, so you can measure starting from a 50 mm, which is for the 2-inch sample, all the way to 8-inch full wafer can be mapped. So coming to data points, so it basically you can have at max 1 million data points. The step height can be ranging from 60 nanometer to 500 microns. This is the range within which you can measure your step height using DECTAC tool. And as previously mentioned, this is a level less when you look from the contamination perspective. So this is an example of a 3D mapping which was performed using the DECTAC tool at an NFC. So these are basically the trenches which are formed using silicon etching using TMH as an etchant. The next tool is KMOS Ultrascan. So this is a tool which is used to measure your curvature and stress in a thin film. So it has a 2D as well as a 3D mapping option, and the maximum sample size can go up to 8-inch full wafers. So coming to the capabilities, the scanning is completely reprogrammable, so you can have a different resolution for each and different scan based on the user requirement. So the sample size can range from 1.5 cm to an 8-inch full wafer. So this tool can be used to measure bow, curvature and stress, and you can have various forms or methods of scanning. It could be a line scan, it could be a circular mapping, or it could be a rectangular scan. So since this uses a laser to perform this scanning, so the wavelength of this laser is 660 nanometer, and your surface needs to be reflective so that you get enough reflections for the tool to analyze your curvature or stress. So these are some of the examples of the measurement carried out using KMOS Ultrascan, wherein onto your left you have a curvature scan and onto your right you have a bow height measurement scan. Next, coming to 4-point probe tool. So this is used to measure the sheet resistance of your thin film. It could be the metallic thin film or after your doping process. So this tool is used to measure sheet resistance up to 80 kilo ohms. The sample size can be 1 cm up to 8-inch full wafer, and this is mainly used when you have done any doping or any metallization if you want to characterize its resistivity. So you get the sheet resistance from this tool, then by using the thickness you can calculate the resistivity of your thin film. So below is a representation of how this tool works. So you have got 4 probes which are collinear in nature, and the distance between each probe is around 1 mm. So we supply current at the outer probes and we measure the voltage on the inner probes, and this is how you get the sheet resistance value. So the next tool is MDP Map. So MDP stands for Microwave Detected Photoconductivity. So this is a tool which is used to measure carrier lifetime of your sample. So these are the capabilities of the tool. So you can measure carrier lifetime as well as photoconductivity. The sample thickness can range starting from 10 micrometer up to 20 mm. The sample size can be 1 centimeter up to 12-inch full wafer. So this tool also has a mapping option, so thereby you can map the complete wafer. The spot size that is used in this tool is 0.5 mm and it can be reprogrammable up to 10 mm. There we have got 2 lasers to perform this measurements. So one is a 405 nanometer laser, the other one is 980 nanometer laser. So this tool also has an heating option, so you can perform measurements wherein you can have a look at how the lifetime or the photoconductivity varies with respect to temperature, and this heating option is available up to only 200 degrees Celsius, and the measurement speed is reprogrammable based on the resolution that you have selected. So it can be as less as 5 minutes for measuring a complete 6-inch wafer at a resolution of 1 mm. The lifetime can be in terms of 20 nanoseconds to a couple of milliseconds, can be measured using this tool. This is an example of the measurements carried out using MCP Map tool. So the top left illustrates a starting new silicon wafer, wherein you can see the lifetime is of order of 20 milliseconds. Okay. This slide illustrates an example of the measurements carried out using MCP tool. So wherein on your top left corner you have a silicon wafer measurement, wherein your lifetime of a wafer is in order of 20 microseconds. So this wafer the scan was carried out before an RCA cleaning, wherein after RCA cleaning, if you notice, the lifetime has increased, okay, wherein it's on order of 50 microseconds. And after this RCA cleaning, the wafer was used to perform oxidation, and during the oxidation the lifetime has further increased up to 55 to 60 microseconds. And once you remove this SiO2, you get back your nascent silicon, which is having a lifetime of 120 microseconds. So this exercise was carried out to ensure that the SiO2, the growth that we perform, is actually passivating your silicon. So by this you can understand that when you started from a 20 microseconds, at the end you almost have a 120 to 150 microseconds as your end lifetime. Thereby the SiO2 growth that has happened has actually protected your wafer surface. So this is also a measure of contamination. So if your contamination is higher, your lifetime has a drop in it. So these were the tools which were available at Diffusion and Inline Characterization Bay. So I would like to thank you for your time.